the length of line segment CS equals to the length of line segment OS, this small line segment, is equals to CS minus CO. Okay, so OS equals to CS. CS is actually the radius of the quarter circle because of the fact that line segment CS starts from the center of the quarter circle, that is to say from point C, and ends at point S, that is a point on the quarter circle itself. So CS equals to the radius of the semicircle, that is to say it is equals to 3 units. It is given us the question. So CS equals to 3 units minus CO. We already found out that the diagonal CO square BOCD equals to square root of 2 times R. So CO equals to the square root of 2 times R. Therefore, we actually found out that the length of line segment OS equals to 3 minus square root of 2 R. So we can write down that here the length of line segment CS, it is equal to 3 minus square root of 2 times R. Okay, in the next step we will complete the quarter circle to a semicircle. So we created this circle from the quarter circle, and then we'll extend diagonal CO by a straight line until it touches the circle at this point, point M. So we'll extend line segment OC or diagonal OC by a straight line until it touches the circle at this point. Point M is the touching point of the extended diagonal CO with this circle. So what is the size of line segment MC? C is the center of the circle and also the center of the quarter circle. M is a point on the circle itself. And this is exactly the definition of a radius. That is to say, MC, it is equal to the radius of the quarter circle, that is also the radius of the circle itself, that is equal to 3 units. Okay? In the next step, I will present to you a new rule that is related to two chords that intersect with each other inside a circle. This will be rule number 3, of course. So here This is rule number 3. If we have this circle and we have also two chords that intersect with each other inside this circle, we have here chord, this is chord AB, and we have also chord CD, as you can see in the drawing, chord AB intersects with chord CD at this point. This is the intersection point. We will define the intersection point between chord AB and chord CD as O. And in this case, the following relationship exists between the parts of the two chords. AO times OB will be equal to CO times OD. I repeat again. According to rule number 3, whenever you have two chords that intersect with each other inside the circle, then the following formula is true, that AO times OB equals to CO times OD. Actually, we can implement rule number 3 in our drawing, because in our drawing we have chord MS, or this is chord SM. You can see here, this is chord SM. Intersects with chord FE, with chord FE. At point O. Point O is an intersection point. I'll repeat again. In our original drawing, we have chord SM that intersects with chord FE at point O. Point O is the intersection point of the two chords. Therefore, according to rule number 3, we will get that MO times OS will be equal to FO times OE. I'll repeat again. Because of the fact that in our circle chord SM intersects with chord FE at point O, then according to rule number 3, MO times OS equals to FO times OE. First of all, what is the length of line segment FO? O is the center of the semicircle, F is a point on the semicircle itself, therefore this is exactly the definition of a radius. That is to say, FO equals to the radius of the semicircle that we defined as R. Likewise, for the same reason exactly, OE will be also equal to the radius of the semicircle. Why? Because it starts from the center of the semicircle, that is to say from point O, and that's at point E, that is a point on the semicircle itself. Therefore, OE is the radius of the semicircle, that is to say it is equals to R. Okay, and what is the value of MO? MO, line segment MO, equals to MC plus CO. Again, MO, you can see it from the drawing, that MO equals to MC plus CO. MO equals to MC plus CO. OS, we already found out that OS equals to 3 minus square root of 2R. So MO equals to MC plus CO. OS equals to 3 minus square root of 2R. And it is equal to FO, that is R, the radius of the semicircle, and OE is also R. So in conclusion, we found out that MO equals to MC plus CO. MC equals to 3 units. CO, it is the diagonal of square BOCD, therefore it is equals to square root of 2 times R. So in conclusion, we found out that MO, that is equal to MC plus CO, equals to 3 plus square root of 2R, and OS equals to 3 minus square root of 2R, and it is equal to R times R, that is R squared. Here we have this expression 3 plus square root of 2R times 3 minus square root of 2R, that is very similar to the algebraic identity that A plus B times A minus B equals to A squared minus B squared. Okay, in our specific expression, we know that A equals to 3 and B equals to square root of 2 times R. Okay, and this expression equals to A squared minus B squared. A squared is 3 squared, that is 9, minus B squared. B is square root of 2R, so B squared is square root of 2R squared. Square root of 2R is square root of 2, that is 2, R squared. So in conclusion, we found out that the expression that we have here, 3 plus square root of 2R times 3 minus square root of 2R, it is equal to 9 minus 2R squared, and it is equal, here, according to this equation, it is equal to R squared. Here we will add 2R squared to this equation, and we'll get that 9 equals to R squared plus 2R squared is 3R squared. We'll divide this equation by 3, and we get that R squared equals to 9 over 3, it is 3. So R squared equals to 3. What is the area of the semicircle? We know that the area of a circle is pi R squared, therefore the area of the semicircle will be equal to half of it. That is to say, the area of this semicircle will be equal to pi R squared over 2. Okay, this is the area of the semicircle. Is equal to pi R squared over 2. So it is pi and r squared equals to 3, so we'll substitute r squared by 3 and we'll divide it by 2. In conclusion, the area of the semicircle equals to 3 pi over 2 square units, so in terms of numbers it is equals to 4.71 square units. I'll repeat again. The area of the semicircle, it is equal to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. Okay? We finished with the first method. In the next step, I will present to you how to find out the area of the semicircle according to the second method. This is the first method here. So here, the center of the semicircle is at point O. We will use the same definition that we used in the first method, and we have already found out that quadrilateral OBCD is a square. This quadrilateral OBCD is a square, and the diagonal OC of this square equals to square root of 2 times r. R is the radius of the semicircle, of course. And here we have point F, E, H, we have already found out that line segment FO equals to R, it is the radius of the semicircle, and OE is also equals to R, it is also the radius of the semicircle. In the next step, we will join points C and D together by a straight line. What is the length of line segment CO? We already know that C is the center of the semicircle, C is the center of the semicircle, and E is the point of the semicircle itself. This is exactly the definition of a radius. That is to say, CE is the radius of the semicircle. It is the radius of the semicircle that is given as the question. It is equal to 3 units. So we can write down that CE equals to 3 units because it is the radius of the semicircle. It is the radius of the quarter circle. Okay? We join points C and F together by a straight line. For the same reason exactly, CF will be also equal to the radius of the semicircle, that is to say, CF will be also equal to the radius of the quarter circle, that is to say, it will be equal to 3 units. I'll repeat again on the explanation. Line segment CF starts from point C, that is the center of the semicircle, it is the center of the quarter circle. Point C is the center of the quarter circle, and F is a point on the quarter circle itself. This is exactly the definition of a radius. That is to say, CF is the radius of the quarter circle, that is to say it is equal to 3 units, according to what is given as the question. So actually, triangles FCE is an isosceles triangle. Why? Because side FC equals to side CE. Okay? And actually, FE, line segment FE, is the base of the isosceles triangle. And here, CO is the median to the base FE. Why? Because CO bisects the median because CO, that is the median of the, it is the median to the base FE. Why CO is the median to the base FE? Because of the fact that CO bisects the base FE, CO bisects the base FE into 2 equal parts. That is to say, FO equals to OE equals to R. For that reason, CO is the median to the base FE. So I will copy the isosceles triangle FCE in a new page, and we will analyze this triangle, this isosceles triangle. So this is the isosceles triangle CEF that I copied from the original drawing. And here we have EF. EF is the base of the isosceles triangle CEF. It is the base. I write down that triangle CEF is an isosceles triangle. And EF is the base of the isosceles triangle CEF. And CO is the median to the base. Okay, it is the median to the base, as I already explained. Why it is the median? Because it bisects the base EF into 2 equal parts. EO equals to OF equals to R, the radius of the semicircle. And we also have a new rule that is related to the median of an isosceles triangle, according to rule number 4. Will be rule number 4. According to rule number 4, the median to the base in an isosceles triangle, the median to the base in an isosceles triangle is perpendicular to the base. I will read rule number 4 again. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. So according to rule number 4, the median CO to the base EF in an isosceles triangle CEF is perpendicular to the base EF. That is to say, CO is perpendicular to EF. That is to say, this angle will be equal to 90 degrees according to rule number 4. This angle will also equal to 90 degrees according to rule number 4. Okay, so actually the median to the base in an isosceles triangle creates two right triangles here. The right triangle COE and the right triangle COF. And we will implement, so first of all, according to rule number 4, the median CO to the base FE is perpendicular to the base FE. So CO is perpendicular to FE. That is to say, this angle equals to 90 degrees and this angle will also equal to 90 degrees according to rule number 4. Why? Because the median CO is perpendicular to the base FE. Therefore, this angle will be equal to 90 degrees and this angle will also equal to 90 degrees. So here we will implement the Pythagoras theorem on this right triangle, triangle COF, and we find out the radius of the semicircle COF. So here we'll implement the Pythagoras theorem on this right triangle, triangle COF. So I will copy the right triangle, triangle COF in a new page, and we will implement the Pythagoras theorem on this green right triangle, triangle COF. So this is the right triangle, triangle COF. The right green triangle, triangle COF. So in the right green triangle, triangle COF, according to the Pythagoras theorem, PT is abbreviation for Pythagoras theorem, we will get that the square of the hypotenuse equals to the sum of the squares of the perpendiculars according to the Pythagoras theorem, that is to say CF squared, that is the square of the hypotenuse, equals to the sum of the squares of the perpendiculars, that is to say it is equal to CO squared plus FO squared. Here the hypotenuse CF equals to 3 units, therefore the square of the hypotenuse is CF squared, that is 3 squared, that is 9, and it is equal to CO squared. CO equals to square root of 2r, therefore CO squared is square root of 2r squared. Square root of 2r squared is the square root of 2 squared, that is 2, times r squared of course, plus FO squared. FO equals to r, so FO squared will be equal to r squared. So in conclusion, we found out that 9 equals to 2r squared plus r squared, that is 3r squared. 3r squared, we'll divide this equation by 3 and we'll get that r squared equals to 9 over 3, that is 3. So we found out that r squared equals to 3, and we already found out that the area of the semicircle equals to pi r squared over 2. So it is actually pi. R squared is 3, so we'll substitute r squared by 3 over 2. In conclusion, the area of the semicircle will be equal to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. I repeat again, we actually found out that the area of this semicircle, according to the second method, the area of this semicircle that is inscribed by a quarter circle, it is equal to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. We finished with the first question. In the next step, I will present to you how to find out the angle of the right triangle, triangle ABC. So this is the second question. Angle theta, we'll find out the size of angle theta in 2 different methods. So in the drawing we have the right triangle, triangle ABC. We know that side BC of the right triangle ABC equals to 6 units. We also know that angle ABC equals to 90 degrees. We have line segment DE is perpendicular to the hypotenuse AC of the right triangle ABC. We also know that AE equals to EC. And we want to find out the size of this angle, that is angle BAC, that is equals to theta. We'll find out the size of this angle theta in 2 different methods, so we'll start with the first method. In the first method, the first thing that we will do, actually, we will draw perpendicular from point E on BC. So this angle will be equal to 90 degrees according to our construction. This angle will also equal to 90 degrees according to our construction. We will define the touching point of the perpendicular from point E and BC as F. In the next step, we will define angle ACB as alpha. But because of the fact that triangle ABC is a right triangle, this angle equals to 90 degrees. This angle equals to theta, so the first angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle ABC, 280 degrees. So this angle equals to 90 degrees minus theta. So because of the fact that we defined the size of this angle as alpha, and we all just right now we found out that this angle is also equal to 90 degrees minus theta, we'll conclude from it that alpha equals to 90 degrees minus theta, of course. So we can write down that angle alpha equals to 90 degrees minus theta. Here we will add to this equation theta and we will subtract alpha, and we'll get that theta equals to 90 degrees minus alpha. In triangle FEC, this small right triangle, we know that this angle equals to 90 degrees. This angle equals to alpha. Therefore, the third angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in triangle FEC, 280 degrees. This is equals to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to theta. So we can write here that this angle that is equal to 90 degrees minus alpha, it is actually equals to theta. Okay? In the next step, we will find out the size of this angle, angle DEF. Angle DEF. What is the size of angle DEF? It is very easy to see from the drawing that the size of angle DEF will be equal to the size of the big angle that is actually angle DEC minus the size of this angle that is FEC. So angle DEF will be equal in size to the big angle, angle DEC, that is equal actually to 90 degrees, according to what is given as the question, minus the size of this angle that is actually angle FEC. The size of this angle is actually equal to 90 degrees minus alpha. So minus angle FEC. I repeat again, we just right now found out that the size of angle DF equals to the size of the big angle that is angle DFC minus the size of angle EFC. So the size of angle DEF is equal to angle DFC, the big angle, angle DFC equals to 90 degrees according to what is given as the question, minus the size of this angle, angle FEC, that is equal to 90 degrees minus alpha. So the size of angle DEF is equal to 90 degrees. We'll open the brackets here and we'll get that 90 degrees minus 90 degrees is 0. Minus and minus is plus, so it is plus alpha. So in conclusion, we found out that angle DEF is equal to alpha. Angle DEF equals to alpha. Here, the missing angle, angle DEF equals to alpha. So in the right triangle, triangle DEF, this angle equals to 90 degrees. This angle equals to alpha, so this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in the right triangle DEF to 180 degrees. Okay? But, so this angle equals to 90 degrees minus alpha. But we have already found out that 90 degrees minus alpha equals to theta. Okay? So we'll substitute here this angle that is actually equals to 90 degrees minus alpha by theta. Okay? In the next step, we will prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle FEC. This small right triangle, triangle FEC. So why those two right triangles are similar to each other? So I will write it down. Triangle ABC, the big right triangle, is similar to the small right triangle, triangle FEC. So why those two right triangles are similar to each other? First of all, those two angles, they are equal to each other, they are both equal to 90 degrees. So angle ABC this angle of triangle ABC is equal to this angle, angle EFC of triangle EFC, and both those two angles are equal to 90 degrees. Okay, I will repeat again. Angle ABC equals to angle EFC, and both angles are equal to 90 degrees. In addition, we have those two angles, they are both equal to theta, therefore they are equal to each other. That is to say, angle BAC this angle, it is equal to angle FEC this angle, and both angles are equal to theta. Okay, I'll repeat again. Angle BAC equals to angle FEC, and both angles are equal to theta. Finally, this angle, angle alpha, belongs to both triangles. It is a common angle. So we can write down that this angle equals to itself. Or in other words, we can write down that angle BCA of triangle ABC is equal to angle FCE, and both angles are equal to alpha. It is the same angle that we called the same angle two different names. So this angle equals to itself, and they are equal to each other because we are talking about a common angle. I'll repeat again. Angle BCA equals to angle FCE equals to alpha. It's a common angle that belongs to both triangles. It is very easy to see that this angle alpha belongs to triangle ABC, the big right triangle, and it also belongs to the small right triangle, triangle FEC. So actually prove that all the angles of triangle ABC can relate to all the angles of triangle FEC. Those two angles are both equal to 90 degrees. Those two angles are both equal to theta, and this angle is a common angle that belongs to both triangles. So we can write down that the right triangle, triangle ABC, is similar, this is the sign of similar, to the right triangle, triangle FEC, according to angle similarity rule. Okay? And from the fact that those two right triangles are similar to each other, we conclude hence that AB over AC, AB over AC, AB over AC, the right triangle ABC, is equal to FE over EC in the right triangle FEC. I will repeat again. From the fact that the right big triangle ABC is similar to the right small triangle FEC, we will conclude that the following relationship exists between their sides, that AB over AC in triangle ABC is equal to FE over EC in the small right triangle FEC. Okay, here we will define side AE as A. We define side, so if AE equals to A, and it is given as the question that AE equals to EC, therefore EC must be also equals to A. Okay? We define side, here side EF as X, and side EF as Y. So here we found out that according to equation number 1, AB over AC, so it is AB over AC. What is the length of the hypotenuse AC? According to our definition, the length of the hypotenuse AC equals to A plus A, that is 2A. And it is equal to EF. EF, according to our definition, is Y over EC. EC, according to our definition, is A. So, in conclusion, according to equation number 1, we found out that AB over 2A equals to Y over A. Here we have A on both sides of equation number 1, so A will get cancelled, and we left with, according to equation number 1, AB over 2 is equals to Y. Here we will multiply equation number 1 by 2, and we'll get that AB equals to 2Y. AB equals to 2Y, so we can write down here that AB equals to 2Y. In the next step, we will prove that the right big triangle, triangle ABC, is similar to the right small triangle, triangle EFD, this right triangle. So why those two right triangles are similar to each other? Triangle ABC, the right big triangle is similar to the right small triangle, triangle DEF. First of all, we know that those two angles, they are equal to each other, they are both equal to 90 degrees. So we can write down that angle ABC of triangle ABC is equal to this angle that is actually angle EFD of triangle EFD, and both angles are equal to 90 degrees. I'll repeat again. Angle ABC is equal to angle EFD, and both angles are equal to 90 degrees. In addition, those two angles, they are equal to each other, they are both equal to alpha. So angle BCA in triangle ABC is equal to this angle that is actually angle DEF, and both angles are equal to alpha. I repeat again. Angle BCA equals to angle DEF, and both angles are equal to alpha. Finally, we have those two angles, they are both equal to theta. So we can write down that angle BAC of triangle ABC is equal to angle EDF of triangle EDF, and both angles are equal to theta. I will repeat again. Angle BAC equals to angle EDF, and both angles are equal to theta. So we actually proved that all the three angles of triangle ABC can point to all the angles of triangle EDF. Why? Because both those two angles are equal to theta, both those two angles are equal to alpha, and both those two angles are equal to 90 degrees. Therefore, we can write down that the right big triangle ABC is similar to the right small triangle DEF, and they are similar to each other according to angle similarity rule. And from the fact that the right big triangle ABC is similar to the right small triangle EFD, we will conclude hence that AB over BC, this will be question number 2, AB over BC is equal to DF over FE. I'll repeat again. From the fact that triangle ABC is similar to triangle DFE, we will conclude that AB over BC equals to DF over FE. Here AB equals to 2y, so we substitute AB by 2y. Over BC. BC equals to 6 units according to what is given as the question. And it is equal to DF equals to x according to our definition, over FE that is equal to y according to our definition also. So in conclusion, we found out that 2y over x equals to x over y. Here we will divide both the numerator and the denominator on this side of equation number 2 by 2. And we will get that according to equation number 2, 2y over 2 is y, and 6 over 2 is 3, and it is equal to x over y. Here we cross multiply this equation number 2, and we get that y squared equals to 3x. According to equation number 2, y squared equals to 3x. And if we focus on the right small triangle EDF here, in the right small triangle EDF, according to the Pythagoras theorem by PT, we get that x squared plus y squared equals to 2 squared. Question number 3 says that x squared plus y squared equals to 2 squared, that is 4. Here, in the right triangle EDF, according to equation number 3 and by Pythagoras theorem, we get that x squared plus y squared equals to 4. So here we can substitute y squared in equation number 3 by 3x from equation number 2, because 3x equals to y squared. We do it now, and we get that x squared plus y squared is 3x, according to equation number 2, equals to 4. Here we subtract 4 from this equation number 3, and we get that according to equation number 3, we get that according to equation number 3, x squared plus 3x minus 4 equals to 0. So here we have a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for, and we find out the value of x according to the following formula. X equals to minus b plus minus square root of b squared minus 4 times ac over 2a in our specific quadratic equation. the coefficient A equals to 1, the coefficient B equals to 3, and the coefficient C equals to minus 4. So we'll put the data inside the formula for x, and we'll find out the value of the values of x. So here we'll get that x equals to minus b, b equals to 3, so minus b is minus 3, plus minus square root of b squared. B is 3, so b squared is 3 squared, that is 9. Minus 4 times a is 1, and c is minus 4. Over 2a, a is 1, so 2 times 1 is 2. So here we got that x equals to minus 3 plus minus here minus 4 times minus 4 is 16, and 16 plus 9 is 25, so inside the root what is left is only 25 over 2. So we actually got that x equals to minus 3 plus minus square root of 25 is 5 over 2. So here we have two solutions that are possible for x. The first solution for x is x1 equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8, and minus 8 over 2 is minus 4. So we found out that x1 equals to minus 4. And here, because of the fact that x is the length of side df, it must be a positive number. X is the length, and therefore it must be a positive number. That is to say, x can never be equal to minus 4, so we will cancel this solution, and we're left only with the second solution, x2, that is equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So we found out that x2 equals to 1. So in the next step, I will copy the right triangle DEF in this page, and we will implement the Pythagoras theorem on the right triangle DEF. So this is the right triangle DEF. This is the right triangle DEF. Here, cosine theta equals to df over de. So cosine theta equals to df, that is 1, because x equals to 1, over de, that is 2, it is given as the question. So in conclusion, we found out that cosine theta equals to 1 over 2, and if cosine theta equals to 1 over 2, it means that theta itself equals to 60 degrees. So the answer to the question is that angle theta itself equals to 60 degrees. Angle theta equals to 60 degrees. This is the answer to the question. Okay, in the next step, I will present to you how to find out the size of angle theta according to the second method. In the second method, we will define this angle as angle alpha, and here we know that in the right triangle ABC, this angle equals to 90 degrees, this angle equals to theta, so this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle ABC, 280 degrees. This angle must be equal to 90 degrees minus theta. And we will define line segment AE as A, and EC will be also equal to A, and we will focus on the right triangle ABC. I will copy the right triangle ABC in a new page, and we will analyze the right triangle ABC. AC, the hypotenuse AC equals to A plus A, that is 2A according to our definition. So this is the right triangle ABC that I copied from the original drawing. Here in the right triangle ABC, we know that cosine alpha equals to BC over AC. BC equals to 6 units, it is given as the question, and AC equals to 2A according to our definition. Here we divide both the numerator and the denominator of this side of the equation by 2, and we get that 6 over 2 is 3, and 2A over A is A. So in conclusion, we found out that according to equation number 1, cosine alpha equals to 3 over A. Here we will multiply equation number 1 by A, and then we will divide it by cosine alpha, and we will get that according to equation number 1, A equals to 3 over cosine alpha. Okay, in the next step we will focus on the right triangle CED. So I'll copy the right triangle CED and we'll analyze the triangle. and complete the right triangle CDE in this new page. Here we know that tangents alpha, this will be question number 2, equals to DE over EC. So tangents alpha equals to DE, that is 2, over EC, that is A. So in conclusion, we found out that tangents alpha, according to equation number 2, equals to 2 over A but according to equation number 1, we have already found out that A equals to 3 over cosine alpha. Therefore, we can substitute A in equation number 1, and we can substitute A in equation number 2 by 3 over cosine alpha for equation number 1. We'll do it now, and we get that according to equation number 2, tangents alpha equals to 2 over A, and A equals to 3 over cosine alpha according to equation number 1. So according to equation number 2, we found out that tangents alpha equals to 2 times cosine alpha over 3. We know that tangents alpha equals to sinus alpha over cosine alpha, so we can substitute sinus alpha in equation number 2 by sinus alpha over cosine alpha. Sinus alpha over cosine alpha. And it is equal to 2 times cosine alpha over 3. Here we cross multiply this equation number 2, and we get that according to equation number 2, two times sine alpha equals to 2 times here we have tangent alpha equals to 2 times cosine alpha over 3. So it is actually 2 times cosine alpha over 3. Because multiply this equation, and we found out that 3 times sinus alpha equals to 2 times cosine square alpha. Actually, we have the trigonometric identity that states that sine square alpha plus cosine square alpha equals to 1. We subtract sine square alpha from this equation, and we get that cosine square alpha equals to 1 minus sine square alpha. So here we can substitute cosine square alpha in equation number 2 by 1 minus sine square alpha. We'll do it now, and we get that according to equation number 2, three times sine alpha equals to 2 times cosine square alpha, but cosine square alpha equals to 1 minus sine square alpha according to this trigonometric identity. So we got that 3 times sine alpha equals to, we'll open the brackets here, 2 times 1 is 2, and 2 times 1 square sine square alpha equals to minus 2 times sine square alpha. We'll add 2 sine square alpha to this equation, and we get that equation number 2, and we get that according to equation number 2, 2 sine square alpha plus 3 sine alpha equals to 2. Here we'll subtract 2 from this equation, equation number 2, and we get that according to equation number 2, 2 sine square alpha plus 3 sine alpha minus 2 equals to 0. So here we have a quadratic equation. The coefficients of this quadratic equation are as follows. A is equal to 2, B is equal to 3, and C is equal to minus 2, and the general formula to find out the missing variable in a quadratic equation is x equals to minus b plus minus square root of b squared plus 4 times ac over 2a. The variable that we are looking for is sinus alpha, so x is equal to sinus alpha. So we'll put the data inside the equation for x, the formula for x, and we find out the value of the values of sinus alpha because x equals to sinus alpha. So we get that sinus alpha equals to minus b equals to 3, so minus b is minus 3, plus minus square root of b square is 3, so b square is 3 squared, that is 9, minus 4 times a is 2, times c it is minus 2, over 2a. A is 2, so 2 times 2 is 4. So we found out actually that sinus alpha is equal to minus 3 plus minus square root of minus 4 times minus 2 is minus 8, it's minus 8 times minus 2 is plus 16, 16 plus 9 is 25. So inside the root we left only with 25 over 4. So here we take a root from the square root of 25 is 5, so in conclusion we found out that sinus alpha equals to minus 3 plus minus 5 over 4. So here we have two solutions that are possible for sinus alpha. The first solution for sinus alpha is that sinus alpha equals to minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8, and minus 8 over 4 is minus 2. So in conclusion, we found out that according to the first solution, sinus alpha equals to minus 2. But because of the fact that the range of values that sinus alpha can accept, the function sinus can accept the ranging from -1 to +1, and -2 exceeds this range of values that sinus can accept. Therefore, that is to say, sinus alpha can never be equal to -2. So we cancel the solution and we're left only with the second solution, that sinus alpha equals to -3 plus 5 over 4. -3 plus 5 is 2, and 2 over 4 is 1 over 2. So we found out that sinus alpha equals to 1 over 2. And if sinus alpha equals to 1 over 2, it means that alpha itself must be equal to 30 degrees. So we found out that alpha equals to 30 degrees. And we have already found out that here alpha equals to 90 degrees minus theta. So we can write down that alpha equals to 90 degrees minus theta. We substitute alpha by 30 degrees because alpha equals to 30 degrees, and we get that 30 degrees equals to 90 degrees minus theta. Here we will add theta to this equation and we subtract 30 degrees, and we get that theta equals to 90 degrees minus 30 degrees. 90 degrees minus 30 degrees is 60 degrees. So we found out that the size of angle theta is equal to 60 degrees according to the second method also. So here we found out that angle theta equals to 60 degrees. So actually we finished with the second method of the second question. In the next step, I will summarize the lecture. We start with the first question. Okay. In the first question, we have a semicircle that is inscribed by a quarter circle, and we know that the radius of the quarter circle is equal to 3 units, and we want to find out the area of the semicircle that is inscribed by the quarter circle. So we define the center of the quarter circle, the center of the semicircle as point O, and then I presented to you rule number 1. According to rule number 1, a tangent to a circle is perpendicular to the radius drawn to its point of tangency. So here we have a circle, the center of this circle is point O, and we have tangent AB. This tangent AB is tangent to this circle as point M. Point M is the point of tangency of tangent AB with this circle. So according to rule number 1, a tangent to a circle, that is to say tangent AB, is perpendicular to the radius drawn to its point of tangency. So whenever you have the radius that is drawn to the point of tangency, like in this drawing, the radius ON is drawn to the point of tangency, that is to say it is drawn to point M, that is the point of tangency of tangent AB with this circle. Then, if this is the case that the radius is drawn to the point of tangency, then the tangent will be perpendicular to that radius. Again, the tangent AB will be perpendicular to the radius MO. So AB is perpendicular to MO, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay, so we can implement rule number 1 in our drawing. Right, because here from point O, we draw the radius to the point of tendency, that is point B. Point B is the point of tendency of tangent AC with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, the tangent AC will be perpendicular to the radius BO. That is to say, this angle will be equal to 90 degrees and this angle will be also equal to 90 degrees. Okay, likewise, from point O, the center of the semicircle, we draw radius to the point of tendency, that is point D, that is the point of tendency of tangent CH with this semicircle. And whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, the tangent CH will be perpendicular to the radius DO. So CH is perpendicular to DO, that is to say this angle equals to 90 degrees and this angle will be also equal to 90 degrees according to rule number 1. So we have here two right angles, and we know that the quarter circle ACH, in any quarter circle, here this point must be the center of the quarter circle, that is to say point C is the center of the quarter circle, and this angle ACH must be equal to 90 degrees. So angle ACH equals to 90 degrees. Therefore, in quadrilateral BOCD we have three right angles. 1, 2, 3. And the sum of three right angles is 90 times 3, that is 270 degrees, plus the size of the fourth angle, that is actually angle BOD. In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. We subtracted 270 degrees from this equation and found out that the missing angle BOD equals to 360 degrees minus 270 degrees, it is 90 degrees. So the missing angle, this missing angle BOD equals to 90 degrees. So we actually found out that in quadrilateral BOCD, this quadrilateral, we have four right angles. And any quadrilateral that has four right angles must be at least a rectangle. So we can relate to quadrilateral BOCD as a rectangle. Okay, quadrilateral BOCD is a rectangle, and we have rule number 2, that the opposite sides of a rectangle are equal to each other. So the opposite sides of rectangle BOCD are equal to each other. That is to say, BO equals to CD. Okay, BO equals to CD according to rule number 2, that the opposite sides of a rectangle are equal to each other. But we have already found out that BO equals to R. It is the radius of the semicircle. BO equals to R. So from this equation, R equals to BO equals to CD, we will derive that CD is also equals to R. Here, CD is also equals to R. Likewise, for the same reason, we will get that OD is equals to BC according to rule number 2, that the opposite sides of a rectangle are equal to each other. Okay, here we'll get that OD equals to BO according to rule number 2. But we know that OD equals to R. It is the radius of the semicircle. OD equals to R, so from this equation R equals to OD equals to BC, we will derive that BC is also equals to R. Here BC is also equals to R. That is to say, in quadrilateral BOCD, we have all its sides are equal to each other, they are all equal to R. And it has also four right angles. Therefore, quadrilateral BOCD is not a rectangle, but it is a square. So quadrilateral BOCD is a square. Then we connected together point C and O by a straight line. CO is the diagonal of square BOCD. We will find out the length of diagonal OCO by implementing the Pythagoras theorem on the green right triangle. The green right triangle, triangle OCD. The square of the hypotenuse equals to the sum of the squares of the perpendiculars, that is to say CO square equals to CD square plus DO square. Here, in triangle, the right triangle COD, CO square equals to OD square plus CD square. CO square is CO square, is the missing line segment. DO equals to R, so DO square will be equal to R square, plus CD square. CD equals to R, so CD square will be equal to R square. So in conclusion, we found out that CO square equals to R square plus R square plus R square is 2R square. So in conclusion, we found out that CO square equals to 2R square, we took out of this equation and found out that the length of the diagonal CO of the square, it is equal to square root of 2 times r. Here, the diagonal CO equals in its length to square root of 2 times r. And what is the, here, we extended the line segment CO by a straight line until it touches the circle at point S. Point S is the point of tangency of extended CO with this circle, with this quarter circle. What is the value of line segment, the small line segment SO? SO, from the drawing, it is very easy to see that SO equals to SC minus OC. Again, SC minus OC will be equal to SO. Okay, here, CO or SO equals to CS minus CO. Okay, here, OS equals to CS minus CO. So CSO equals to CS. CS is the radius of the quarter circle because of the fact that line segment CS starts from the center of the quarter circle, that is to say from point C, and ends at point S, that is the point of the quarter circle itself. Therefore, CO, it is the radius of the quarter circle that is equal to 3 units. So SC equals to 3 units. And CO, we already found out that the diagonal CO of square BOCD equals to square root of 2 times R. So we substituted CS by 3 and CO by square root of 2 times R, then we got that the length of line segment OS, the small line segment, is equal to 3 minus square root of 2R. Here, this line segment OS equals to 3 minus square root of 2R. Then we completed the quarter circle to a circle, and then we extended diagonal OC by straight line until it touches the circle at this point, point M. The touching point of the extended CO with the circle is at this point, point M. So what is the length of MC? C is the center of the quarter circle. M is the point on the circle itself. This is exactly the definition of a radius. That is to say, CM is the radius of the quarter circle that is equal to 3 units. Then I presented to you rule number 3. Rule number 3 is related to two chords that intersect with each other inside the circle. We have this circle and chord AB intersects with chord CD at point O. Point O is the intersection point between the two chords. So if this is the situation, then the following formula is true, that AO times OB equals to CO times OD. Again, AO times OB equals to CO times OD. So we can implement rule number 3 in our drawing. Why? Because in our drawing, the chord MS intersects with chord AE at point O. Okay, chord as MS or SM, it is the same. Intersects with chord FE at point O. Point O is the intersection point of the two chords. Therefore, according to rule number 3, we will get that MO times OS will be equal to FO times FO times OE. Again, MO times OS equals to FO times OE. Okay, MO times OS equals to FO times OE, according to rule number 3. What is the value of MO? Line segment MO equals to MC plus CO. MO equals to MC plus CO. OS, we already found out that OS equals to 3 minus square root of 2R. So we substituted OS by 3 minus square root of 2R. OF equals to R, it is the radius of the semicircle, and OE is also equals to R, it is the radius of the semicircle. So FO is R, OE is R, and R times R is R squared. Okay, so MC is 3 units, CO is square root of 2R. Again, MC is 3 units and CO is square root of 2 times R, times 3 minus square root of 2R equals to R squared. Here this expression, it is very similar to the algebraic identity that a plus b times a minus b equals to a squared minus b squared. In our specific expression, a equals to 3 and b equals to square root of 2r. And this expression equals to a squared minus b squared according to this trigonometric identity. A squared is 3 squared, that is 9, minus b squared. B is square root of 2r, so b squared is square root of 2r squared. Square root of 2r squared equals to 2r squared, and minus b squared is minus square root of 2r squared. So this expression equals to 9 minus 2r squared, and it is equal to r squared. So in conclusion, we found out that 9 minus 2r squared equals to r squared. We added 2r squared to this equation and found out that 9 equals to 2r squared plus r squared is 3r squared. We divided this equation by 3 and we got that r squared equals to 9 over 3, that is 3. So we found out that r squared equals to 3, and the area of the semicircle, it is half the area of the circle, and the area of the circle is pi r squared, therefore the area of the semicircle will be equal to pi r squared over 2. So it is pi, r squared is 3, and all divided by 2. In conclusion, we found out that the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equal to 3.71 square units. Okay? We finished with the first method. In the next step, I will present to you how we found out the area of this semicircle according to the second method. According to the second method, we actually used the things that we already found out in the first method, used it in the second method. That is to say, we have already found out that in the first method that BOCD is a square, and the length of the diagonal of the square CO, it is equal to square root of 2r. FO equals to r, it is the radius of the semicircle, and OE, it is also equals to r, it is also the radius of the semicircle. Then we connected points C and E together by a straight line. What is the length of line segment CE? CE, it is actually the radius of the quarter circle. Why? Because CE starts from point C, that is the center of the quarter circle, and ends at point E, that is the point of the quarter circle itself. And this is exactly the definition of a radius. That is to say, CE equals to the radius of the semicircle, that is equal to 3 units according to what is given us the question. From the same reason, we joined points C and F together by a straight line, and CF, line segment CF, will be equal to the radius of the quarter circle, that is 3 units, because it starts from the center of the quarter circle and ends at point F, that is a point on the quarter, circle itself. Therefore, CF, it is the radius of the quarter circle, that is equal to 3 units. So here we created an isosceles triangle. Triangle FCE is an isosceles triangle. Why? Because FC, side FC, equals to side CE, and both sides are equal to 3 units. Okay? And here, in this isosceles triangle FCE, FE is the base of the isosceles triangle, and CO is the median to the base. Why CO is the median to the base? Because CO bisects the base into 2 equal parts. FO equals to OE equals to 1. Okay, for that reason, CO is the median to the base. Okay, and we have also rule number 4. According to rule number 4, the median to the base in an isosceles triangle is perpendicular to the base. Here, I've already explained to you that triangle CEF is an isosceles triangle because of the fact that CE equals to CF. The base of the isosceles triangle, triangle ECF, is EF, that EF is the base of the isosceles triangle is CF. The median to the base is CO because the median CO bisects the base into two equal parts, R and R. And according to rule number 4, the median to the base, that is to say CO, in an isosceles triangle ECF, is perpendicular to the base. The base is EF. So the median CO is perpendicular to the base EF. Again, CO is perpendicular to EF. That is to say this angle equals to 90 degrees and this angle must be also equal to 90 degrees according to rule number 4. Because of the fact that the median CO to the base EF is perpendicular to the base, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees according to rule number 4. Okay, so we can write here that according to rule number 4, the median CO to the base EF is perpendicular to the base EF. That is to say, this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Okay? So then, we copied the right triangle COF. This angle equals to 90 degrees according to rule number 4. This angle will be also equal to 90 degrees according to rule number 4. So we copied the right triangle COF in a new page and we implemented the Pythagoras theorem on the right triangle COF. This is the right triangle COF. Again, this angle equals to 90 degrees according to rule number 4. We have already found out that diagonal CO of the square equals to square root of 2 times R. FO equals to R, it is the radius of the semicircle, and CF, it is the radius of the quarter circle that is equal to 3 units. So according to the Pythagoras theorem, in the right triangle CFO, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. That is to say, CF square equals to CO square plus FO square. Again, CF square equals to CO square plus FO square. Here CF equals to 3, so CF square will be equal to 3 squared, that is 9, and it is equal to CO square. CO equals to square root of 2R, and CO square equals to square root of 2R square. The square root of 2 is 2 times R square. Okay? Then the square root of R is R square. So in conclusion, the square root of square root of 2R square, it is equal to 2R square plus FO square. FO equals to R, so the square root of R is R square. So in conclusion, we found out that 9 equals to 2R square plus R square. 2R square plus R square is 3R square. So we actually found out that 9 equals to 3R square. We divided this equation by 3 and we got that R square, 3R square over 3 is R square, and R square equals to 9 over 3, that is 3. So we found out that R square equals to 3, and the area of the semicircle equals to pi R square over 2. So it is equal to pi, and R square is 3, so we can substitute R square by 3. We did it, and we got that pi R square is 3 pi, all divided by 2. So in conclusion, we found out that the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equal to 3.71 square units. Okay, the area of the semicircle equals to either 3 pi over 2 square units, or in terms of numbers, it is equal to 4.71 square units. We finished with the first question. In the next step, I will present to you how we solve the second question. In the second question, we have the right triangle ABC, and get ABC equals to 90 degrees. Side BC of the right triangle ABC equals to 6 units. Line segment DF is perpendicular to the hypotenuse AC. That is to say, this angle equals to 90 degrees and this angle also equals to 90 degrees. We also know that AE equals to EC. and we want to find out the size of this angle, angle theta. Actually, angle BAC equals to angle theta, and we want to find out the size of the angle theta. So the first thing that we did in the first method, in order to find out the size of this angle, angle theta, we made a construction from point E. We draw perpendicular on BC. So this angle equals to 90 degrees, and this angle will also equal to 90 degrees according to our construction. We defined the touching point of the perpendicular from point E and BC as F, and we defined angle ACB as alpha. But actually, in the right triangle, triangle ABC, this angle equals to 90 degrees. This angle equals to theta according to what is given as the question. So this angle must be equal to 90 degrees minus theta in order to complete the sum of the angles in the right triangle ABC, 280 degrees. Why? Because 90 degrees minus theta plus theta is 90 degrees, and 90 degrees plus 90 degrees, it is 180 degrees. 180 degrees. So for that reason, this angle must be equal to 90 degrees minus theta. So according to our definition, this angle equals to alpha. But we know that this angle must be also equal to 90 degrees minus theta. In conclusion, we can say that alpha equals to 90 degrees minus theta. Alpha equals to 90 degrees minus theta. We added to this equation theta, and then we subtracted we added to this equation theta, and then we subtracted alpha from this equation, and we got that angle theta equals to 90 degrees minus alpha. So here we have this angle equals to alpha. So in the right triangle FEC, the right small triangle, this angle equals to 90 degrees. This angle equals to alpha, so this angle must be equal to 90 degrees minus alpha in order to complete the sum of the angles in the right triangle FEC, 280 degrees. This angle must be equal to 90 degrees minus alpha. So what is the size of angle DEF? The size of this angle? The size of this angle DEF will be equal to the size of the big angle, angle DEC, minus the angle FEC. So angle DEC minus angle FEC will be equal to angle DEF. It is very easy to see it from the drawing. Okay, I repeat again. Angle DEF equals to angle DFC, the big angle, minus angle FEC. So here, this angle equals to angle DEC, that is a right angle, according to what is given as the question. It is equal to 90 degrees, minus the size of this angle, that is equal to 90 degrees minus alpha. So it is 90 degrees minus 90 degrees minus alpha. We opened the brackets here and found out that this, the missing angle, equals to DF, it is equal to 90 degrees, minus 90 degrees, minus and minus is plus, so it is 90 degrees minus 90 degrees, that is 0, minus and minus is plus, so in conclusion found out that this angle equals to alpha. So in the right triangle DFE or DEF, if this angle equals to alpha and this angle equals to 90 degrees, this angle must be equal to 90 degrees minus alpha. But we know that 90 degrees minus alpha equals to theta, so we can substitute 90 degrees minus alpha by theta. We did it, so we defined this angle as angle theta, that is equal to 90 degrees minus alpha. Okay, then we defined AE as A, EC will be also equal to A because A equals to EC. We defined DF as X and EF as Y. Then we proved that the right triangle ABC is similar to the right small triangle FEC. Okay, so why those two right triangles are similar to each other? First of all, those two angles, they are equal to each other, they are both equal to 90 degrees. Those two angles, they are also equal to each other, they are both equal to theta. And this angle is a common angle, it belongs to both triangles. So we actually proved that all the angles of triangle ABC can go into all the angles of this right triangle, triangle EFC. Therefore, we proved that the right triangle ABC is similar to the right triangle FEC according to angle similarity rule. Now repeat again. We proved that the right triangle ABC is similar to the right triangle FEC according to angle similarity rule. And from the fact that those two right triangles are similar to each other, we will conclude that AB over AC equals to FE over AC. I'll repeat again, we will conclude that AB over AC equals to FE over AC. Okay, AB is AB, AC is equals to A plus A, that is 2A, so we substitute that AC by 2A. EF equals to Y according to our definition, so we substitute EF by A, and EC equals to, EC is also equals to A according to our definition. So in conclusion, we found out that AB over 2A equals to Y over A. We have A on both sides of the equation, so A will get cancelled, and we're left only with AB over 2, that is equal to Y. We multiplied the equation number 1 by 2, and we got that AB equals to 2Y. So we can write here that AB equals to 2Y. Then we proved that the right big triangle ABC is similar to the right small triangle, this small right triangle, triangle EDF. So why those two right triangles are similar to each other? First of all, those two angles are equal to each other, they are both equal to theta. Those two angles are also equal to each other, and they are both equal to 90 degrees. And those two angles are also equal to each other, and they are both equal to alpha. So we proved that all the angles of triangle ABC can go into all the angles of the right triangle EDF. Therefore, we proved that triangle ABC is similar to triangle DEF according to angle similarity rule. From the fact that those two right triangles are similar to each other, we conclude that AB over BC equals to DF over EF. Again, AB over AC equals to EF. Here, it is here. AB over BC equals to DF over EF. Again, AB over BC equals to DF over EF. AB equals to 2Y. BC equals to 6 according to what is given as the question. DF equals to X according to our definition. And EF equals to Y also according to our definition. So in conclusion, we found out that 2Y over 6 equals to X over Y. Here we divided both the numerator and the denominator by 2. 2Y over 2 is Y, and 6 over 2 is 3. So here we have 3 over Y over 3, that is equal to X over Y. We just multiplied this equation number 2, and we found out that Y squared equals to 3X. So in the right triangle, triangle DEF, it is very easy to see that according to the Pythagoras theorem, X squared plus Y squared equals to 2 squared. Okay? So according to equation number 3, in the right triangle DEF, we know that X squared plus Y squared equals to 2 squared, that is 4. So we can substitute Y squared in equation number 4 by 3X, because Y squared equals to 3X according to equation number 2. We did it, and we got that X squared plus Y squared, that is 3X, equals to 4. We subtracted 4 from this equation number 3, and we got that according to equation number 3, X squared minus 4X, X squared minus 3X, X squared plus 3X minus 4 equals to 0. So we have here a quadratic equation, and the general formula for a quadratic equation is ax squared plus bx plus c equals to 0. Here a, b, and c are the coefficients of the quadratic equation, and x is the variable that we are looking for. And we will find out the value of x according to the following special formula, that x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the coefficient a equals to 1, the coefficient b equals to 3, and the coefficient c equals to minus 4. So we put the data inside the equation for x, and we found out the value of the values of x. Here x equals to minus b, b equals to 3, so minus b is minus 3, plus minus square root of b squared. B equals to 3, so b squared is 3 squared, that is 9, minus 4 times a is 1, times c, that is minus 4, over 2a. A is 1, so 2 times 1 is 2. And inside the root we have minus 4 times minus 4 is 16, and 16 plus 9 is 25. So in conclusion, we found out that x equals to minus 3 plus minus square root of 25 over 2. The square root of 25 is 5. So in conclusion, we found out that x equals to minus 3 plus minus 5 over 2. So here we have two solutions that are possible for x. The first solution for x is x1 equals to minus 3 minus 5 over 2. Minus 3 minus 5 is minus 8, and minus 8 over 2 is minus 4. So the first solution is that x equals to minus 4. But because of the fact that x is a length, it is the length of side df, it must be a positive number. And we got x1 that is minus 4, that is a negative number. Therefore, this solution is incorrect solution. We cancel this solution, and we left only with the second solution, that x2 equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2, and 2 over 2 is 1. So we found out that x equals to 1. So I copied the right triangle DEF, and we found out the cosine theta in the right triangle EDF. This is the right triangle EDF that I copied from the original drawing. We know that EF equals to y, the hypotenuse ED equals to 2, and this DF equals to 1, that is x equals to 1. So here cosine theta, we know that this again equals to theta, so cosine theta equals to DF over EF. Cosine theta equals to DF over ED. Again, cosine theta equals to DF over ED. DF equals to 1. DE or ED equals to 2. So in conclusion, we found out that cosine theta equals to 1 over 2. And if cosine theta equals to 1 over 2, it means that theta itself equals to 60 degrees. So the answer to the question is that the size of angle theta in the right triangle ABC, it is equal to 60 degrees. We finished with the first method. Then I presented to you how to find out the size of angle theta according to the second method. In the second method, we define this angle as alpha. We defined AE as A. EC will be also equal to A. Then we focus on the right triangle ABC. Here, this angle also equals to 90 degrees minus theta. Therefore, we actually can conclude from it that alpha equals to 90 degrees minus theta, exactly as we did in the first method. Okay. Then I copied the right triangle ABC in a new page, and we implemented we actually found the cosine of angle alpha. Angle alpha is equal to angle alpha according to our definition. PC equals to 6 units according to what is given as the question, and angle ABC equals to 90 degrees according to what is given as the question. AC equals to A plus A according to our definition. That is to say, AC equals to A plus A, that is 2A. So here, cosine alpha in triangle ABC will be equal to BC over AC. BC equals to 6, AC equals to 2A. So in conclusion, we found out that cosine alpha equals to 6 over 2A. We divided both the numerator and the denominator by 2. 6 over 2 is 3, and 2A over 2 is A. So here, 6 over 3 is 2, and 2A over 2 is A. So in conclusion, we found out that cosine alpha equals to 3 over A. Here we multiplied equation number 1 by alpha, and then we divided it by cosine alpha, and we found out that according to equation number 1, A equals to 3 over cosine alpha. Then we focused on the right small triangle DEC. So I copied the right small triangle in a new page, and we analyzed the right triangle DEC. In the right triangle DEC, we know that here we know that EC equals to A according to our definition, DC equals to 6 according to what is given as the question, and DE also equals to 2, DE equals to 2 according to what is given as the question. So here tangent alpha will be equal to dE over EC. Tangent alpha equals to dE over EC, dE equals to 2, EC equals to A, so in conclusion we found out that tangent alpha equals to 2 over A, according to equation number 2, but according to equation number 1, we have already found out that A equals to 3 over cosine alpha. That is to say, we can substitute A in equation number 2 by 3 over cosine alpha. We did it, and we got that according to equation number 2, tangent alpha equals to 2 over A, and A is 3 over cosine alpha. So here, from here we found out that tangent alpha equals to 2 times cosine alpha over 3. Tangent alpha equals to sinus alpha over cosine alpha, so we substitute the tangent alpha by sinus alpha over cosine alpha. Then we cross multiply this equation, equation number 2, and we got that 3 times sinus alpha equals to 2 times cosine square alpha. Okay? And here we have the trigonometric identity that states that sine square alpha plus cosine square alpha equals to 1. We subtracted sine square alpha from this trigonometric identity, and we got that cosine square alpha equals to 1 minus sine square alpha. That is to say, we can substitute cosine square alpha in this equation, equation number 2, by 1 minus sine square alpha. We did it, and we got that 3 times sine alpha equals to 2 times, and cosine square alpha equals to 1 minus sine square alpha according to this trigonometric identity. Here we open the brackets, and we got that 3 times sine alpha equals to 2 times 1 is 2, and 2 times minus sine square alpha equals to minus 2 times sine square alpha. We added 2 times sine square alpha to this equation, equation number 2, and we got that 2 times sine square alpha plus 3 sine alpha equals to 2. We subtracted 2 from this equation, equation number 2, and we got that 2 times sine square alpha plus 3 times sine alpha minus 2 equals to 0. So we have here a quadratic equation, and the coefficient of the quadratic equation is A equals to 2, B equals to, the coefficient B equals to 3, and the coefficient C equals to minus 2. So here we have, those are the coefficients of our specific quadratic equation, and the general formula for solving a quadratic equation, as I've already showed you in the first method, x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. In our specific quadratic equation, the variable that we are looking for, x is equal to sinus alpha. So we put the data inside the formula for x, and we find out the value of the values of sinus alpha, because in our specific quadratic equation, the variable that we are looking for is sinus alpha. So x equals to sinus alpha, and sinus alpha equals to minus b, b equals to 3, so minus b equals to minus 3, plus minus square root of b squared, b equals to 3, so b squared is 3 squared, that is 9, minus 4 times ac, minus 4 times a is 2, times c, that is minus 2, over 2a, a is 2, so 2 times 2 is 4. So in conclusion, we found out that sinus alpha equals to minus 3 plus minus, here minus 2, minus 4 times 2 is minus 8, and minus 8 times minus 2 is plus 16, 16 plus 9 is 25. So inside the root we have only 25 that is left. So in conclusion, we found out that sinus alpha equals to minus 3 plus minus square root of 25 over 4. The square root of 25 is 5. So in conclusion, we found out that sinus alpha equals to minus 3 plus minus 5 over 4. So you will have two solutions for sinus alpha. The first solution for sinus alpha is that sinus alpha equals to minus 3 minus 5 over 4. Minus 3 minus 5 is minus 8, and minus 8 over 4 is minus 2. So in conclusion, we found out that sinus alpha equals to minus 2. But because of the fact that the function sinus can accept values that are ranging from minus 1 to plus 1, and minus 2 exceeds this range of values that sinus can accept, this solution is incorrect solution, that is to say sinus alpha can never be equal to minus 2. Therefore this solution is incorrect solution. So we'll cancel this solution and we're left only with the second solution, that sinus alpha equals to minus 3 plus 5 over 2. Minus 3 plus 5 is 2 and 2 over 4 is 1 over 2. So if sinus alpha equals to 1 over 2, it means that alpha itself equals to 30 degrees. And according to this equation, we know that alpha equals to 90 degrees minus theta. Here alpha equals to 90 degrees minus theta. Here we can substitute alpha by 30 degrees because alpha equals to 30 degrees. So we substituted alpha by 30 degrees and we found out that 30 degrees equals to 90 degrees minus theta. Here we added theta to this equation and we subtracted 30 degrees and we got that angle theta equals to 90 degrees minus 30 degrees. 90 degrees minus 30 degrees, it is 60 degrees. So we found out in the second method also that the size of angle theta, this angle, it is equal to 60 degrees. Okay, so in both methods we found out that the size of angle theta, it is equal to 60 degrees. Okay, thank you very much.